זה היה כמו מחשב. אני כאילו נתן לי רוצה לגזור. לא זה כדאי, אתה יודע, אני קצת ואני טוב אני שקו, ואני חכו מה שאני מוכיס לך שיכול תודה, לא לשאול ואני פחד שבמבחן ואני קצת פגר זה עכשיו להתחיל למצוא שונות של משתנה מקרי ידוע, בינומיות, משהו. אתה יודע, באינטרנט, בקיפד, כתוב לך משהו, אז אפשר להתחיל לחשב מטובלת של זה ברגע. אז באמת כזה, לא ששיגעתי. מאוד אוהב. יש מלא. אז מאוד קשה שיהיה לך כמה דוגמאות אחרים.
הוא מריץ את גם תוך כדי, יש לך גרפים, הוא גם ישים לך את הגרפים בקוד.
ברור?
כן, כן.
אבל בתור מה? בתור תמונה כזה?
כן, כאילו, לא, כן, בתור תמונה, הגרפים תמונה, ובתור זה, אתה עושה את זה יפה.
כן?
כן, וכאילו, אתה יודע, כזה צבעים שונים, אז איזה הערות זה ירוק.
אני פשוט פעם כזה כאילו שזה שומר על עיצוב מקור, ואז זה לוקח עם הירוק וכל זה.
איך אתה עושה?
זה כזה, שהפליק הזה יכול לא לשמור חלק סביבה, ואז זה כאילו לוקח את העיצוב של וורד, או שאתה לוקח את העיצוב המקורי.
כן.
אז זה כתוב לזה.
בקיצור, הבעיה שלי, בגלל שמוריד את זה, אז אם נגיד יש לך איזשהו זה מצב לך
טוב, אבל אז אתה יכול כאילו, לעשות כאילו לפני הגרף, לשחק את זה, כאילו, טוב? נו, אז מעולה, אני רציתי את דניאל, זה בעיה, חצי עוד תמונה,
פה?
למה? זה לא וורד?
לא, זה כמו ביד.
Last week, I showed you on a system that combines a sigmoid and a line how we find the fixed point, and we draw the bifurcation diagram. And we found that it was a pitchfork bifurcation. It was the following system. Okay, and we said that depending on beta, we might have 1 or 3 fixed points. What I showed is that when we plot the two components of this function, we have the line which is always the same, but depending on beta, we might have 3 fixed points, right? If the slope of the sigmoid is steep enough, or we might have 1 fixed point if the slope of the sigmoid is very shallow, so it does not intersect with the line before reaching its asymptotic behavior. So we could plot a rough bifurcation diagram. Let's use color for this. Do it in red. Oh. Okay, this is a dashed line. At beta equals 2, this becomes stable, and we have 2 branches appearing. Okay, and we reached the value of, okay, I don't know if I showed this, but the slope here is beta equals beta over 4. The slope of the sigmoid. And the slope of the line is always 1/2. Okay, this is the slope here. So for our critical beta, we can write this, and then we have critical beta equals 2. So this is the approach of finding a critical value of the bifurcation parameter. Now, we'd like to do more than this. We'd like to get the actual expression for these curves. Okay? And for this, of course, we are looking for fixed points. Remember, the curves give us the fixed points as a function of beta. So the way to do this is to demand this. And so we can write x plus 1 over 2 equals 1 over 1 plus an exponent. This is a transcendental equation, and you cannot solve this analytically for x. But what you can do is solve for beta. Okay, instead of solving for x, you can just solve for beta and get the inverse function. Yeah?
Explain again, what are you trying to solve?
Yes, I am trying to find expression for this curve, analytical expressions. Okay, so the curves represent fixed points. Right? They can be unstable, they can be stable. So I demand that the time derivative is 0. So these two should be equal to each other. This is what I wrote here. And then I want to solve for x as a function of beta. But I can't do that. So I will get beta as a function of x instead.
Thank you.
Okay? um, okay, so because I want to show a lot of other things today, I will skip the derivation and I will give you the final solution here. 1 over x when you allow, okay, this is for x that is not 0 and also x between minus 1 and 1. Okay? These are conditions that come out during they should come out during the derivation when you do it. And notice that I have here x is not equal to 0. It's because I will want to, that was, no, what?
If it's equal to 0, then this is
Yeah, exactly. So if x is equal to 0, then this is always true, and I can have any value of beta.
I'm sorry?
And beta is not restrained. I can have any value of beta. So x equals 0 is this line. Okay? Yeah, okay. No, this is not a condition here. But x equals 0 leads to any beta. And then here, okay, this gives you it should give you a kind of a parabola. And you can plot this analytically. And what this gave us is that, for example, these curves are actually asymptotic. Okay? Because x cannot be 1 or minus 1. Okay?
If you plot that, so you get a graph that's what's it called? That's 90 degrees shifted from that, right? So
Yeah.
like an inverse
Yeah.
graph.
Mm-hmm.
And so you just flip it. That's the idea.
What? Yeah, you just tilt it by 90 degrees, or flip it.
Because this is beta in terms of x. So this would be betas on the y-axis. But you want to get a graph like that with x in terms of beta.
Can you show us how do you plot it?
How do I plot it?
Yeah, how do you plot? No, like for example, if you want to do it analytically.
This one?
Yeah.
This is how I plot it. I'll just make a table and try to plot it. So let's do it. It's possible that for negative x. Let's see this. Okay, so x equals 1, 2, 3.
Well, x is only between -1 and 1, right?
Yeah. No, sorry. Yeah, it should be like. Yeah. Let's do x equals 1/4, 1/2, and 3/4. So I got -4, 2. This is 8 over 5. And then this would be -2. Uh, 4. Okay, so I get -4 logarithm of 3/5, -4 logarithm of 1/3 here. And the logarithms are obviously negative, so beta is positive. And so this is a kind of logarithm, but it goes up instead of down. Okay, so going like this. Oh, yeah. Okay. Um, Now it might be that the expression that you will get for a negative x will be slightly different. Okay, but it should reflect this. Maybe have minuses instead of pluses.
So the only additional information we have are the two asymptotes?
No, you can get an exact curve, but only from
Okay.
looking at the big picture, I can already say they're
So
asymptotes, which
before
is
we didn't know the numerical thing,
yeah,
expression.
yeah. You didn't have the numerical expression. Actually, the asymptotes you could actually see them from here. That once the sigmoid is too shallow, it will no longer
I can see it ends somewhere.
yeah, this the crossing should end somewhere. But the idea of this whole example is that sometimes you would like to plot the bifurcation curve, but it will be very hard to solve for x. And then you should try to solve for the bifurcation parameter. Yeah.
Sorry, just taking a step back about the critical data.
Yes?
Can you repeat the calculation?
Yeah. So this line in black is constant. It's always this expression. The sigmoid is what might change according to beta. Okay, so you can imagine the sigmoid being very shallow to begin with, and as beta is changed, as beta is increased, the slope of the sigmoid increases. I found this by doing the derivative of this with respect to x, and finding that at this point it is 1/2. It is is beta over 4. Okay, so as beta is increased, the slope is increased. Okay, until the sigmoid and the line are tangent at this point. Okay, when the sigmoid and the line are tangent, right here. So this is the line, and the sigmoid is tangent here at x equals 0. And it looks like this. So it intersects at exactly one point. But if you increase beta by just a little, it will already intersect at 3 points. Okay, it'll start having these additional intersections. So the condition for the critical case is the tangency of the slope and the line. Okay, I'm going to move to another subject. It's the last one before I show this applied model that I promised. This is called dimensionless analysis. In scaling. And I will explain this more theoretically right now. And in the applied model I show today, we will see how to use it. Okay, so a lot of times it is useful to transform our equations into dimensionless form. And when I say dimensionless, I mean that the variables and the parameters that are used carry no physical units. Okay, I might have an equation where x represents distance, and it is measured in meters. Okay, and the time, I remember I differentiate by time, and that is measured in seconds, right? So these are physical quantities that carry units. Dx over dt equals, for example, x squared, and I'll have a parameter here. And then this is measured in meters. This is measured in seconds. So px squared should be meter per second, right? So I mark this way. When I put square brackets around some expression, it means I'm taking as its units. I'm only saying what units it has. Okay, so x squared, this is the units of x squared, and that's meters square. And so now I know that the dimensions of p should be 1 per meter times second. Okay? Anyway, this is not a dimensionless equation. It has dimensions. The x has the dimension of length. It's measured in meters. T is time. It's measured in seconds. And a lot of times, it will be useful for us when we are analyzing a model to shift the equations into a dimensionless form. When you do this, it first of all makes any mathematical analysis simpler, usually because in the end you end up with less parameters in the equation. And it also allows you to see better. Let's say we have a lot of times we have all kinds of parameters appearing in the equation, and when you reach the dimensionless form, it will be more simple. It will have less parameters, and it will be easier to determine which parts of the equation are the important ones. Okay, because they no longer depend on the parameters so much. We'll see this in a moment. One disadvantage of moving to a dimensionless form is that in your original form of the equation, when you start doing all kinds of derivations of it, and you have many steps, and in the end you reach a very complicated expression. For example, an expression showing you whether the fixed point is stable or not. You can check your derivation by verifying that the final expression holds in the sense of has the right units. For example, in the end, you found that the critical x should be some long expression. You can analyze the units of everything in this expression and see that they all add up to meters. Okay? So this is something that we give up when we move to the dimensionless analysis. Okay, let's return to the logistic equation. Okay, and we want to simplify this as much as possible, reaching some dimensionless form. I'll write here our goal. We want to do all of our analysis on this. Okay, so find some transformation that will take this to this. But it's not always clear what your goal is. Usually you just start the non-dimensionalization and hope to reach an expression as simple as possible. Okay. First, we will look. The first thing you do is you look at the dimensions of all the variables and parameters here. So n has dimensions of population. So we could measure it in individuals. We can invent all kinds of information, all kinds of units for population, like dozens of people, and so on and so on. A kiloperson. Dimension of time, so that could be seconds. Although with a population, we might be interested in days or years. These are just examples. Now, when you try to find out the units of your variables, you should remember that the units should be the same for both sides of the equation. Okay? And when you subtract or add expressions, they must have the same units, right? You cannot add kilograms to meters. They mean different things. So we already know that inside the parentheses here, where we have a subtraction, we should have the same units. Now, if the person who gave you the equation was meticulous enough, then the fact that there is no unit next to the 1 means that this 1 is unitless. Sometimes people neglect this, and then later you find out, oh, this was supposed to be seconds, 1 second. Okay, so this thing should be dimensionless. N over k. When I want to write that there are no units, I would usually write 1. Okay. So this means that the dimensions of k are the same as those of n, and so could measure it in kilopersons, the capacity of the environment. So the parentheses do not give us units. So the units of Rn should be equal to the units of dn over dt, right? So and so R should have a dimension of 1 over time, and that will be 1 over second, or 1 over year, and so on. Okay? And it makes sense because R represents a rate of growth. Okay? Now, I wrote here several examples for each dimension, but in all parts of the equation, you must use, of course, the same units. If you use seconds, you need to be consistent in the whole equation. Sometimes you get equations with constants that allow you to substitute here, for example, something with different units, like substitute it in milliseconds. But then there will be some constant making the conversion. And strictly speaking, the constant should also carry units. Okay?
You said the units of Rn are equal to the units of n over t?
Yeah.
Should it be the units of dn over dt?
It's the same. It's the same.
Okay.
The units of n of dn are the same, and so on. Okay, so one of the things that we learn when we do the dimensionless analysis is we learn what are the relevant scales for the system. For example, for an equation like this, it might not be interesting to look at values of n like 1, 2, 3, right? And instead, we would like to look at 1,000, 2,000, and so on. And for time scales, we would find it useless to look at seconds and instead we will look at days or years. Okay, because there is nothing in this equation that will happen on the order of seconds. And so the first step in the non-dimensionalization would be to look for an appropriate scale. And so I could make up a new variable, tau. This is time, but on the relevant time scale. Okay, this is unitless time. Unitless time. And I write that it's t over some time constant. Okay, so this means that if I used to measure time in seconds, now, okay, this was time in seconds. Now, what I'm interested in is time in minutes, say. Okay? If tau is something on the order of minutes, I kind of stretch my time scale. So now I will be working with numbers that are convenient, like 1/2, 1, 2, 3, instead of working in multiples of like 120, 360, and so on. I'm going to bring everything to a scale of around 1 in this way, and I'm going to talk on a time axis that is already adapted to my system. But I don't know what time constant is correct for this system. Don't know in advance. And just as a comment, what I'm showing here is a method that is kind of more rigorous to do the dimensional analysis. It's also possible to do this heuristically and try to simplify this expression as much as possible. And on the way, you will find the time scale, for example, popping out. Okay? We'll do this with the model I'm showing, I think. We might do it in this method as well. Okay. So I'm also looking for a relevant scale for the population. So I'm going to write the new variable x as n divided by some relevant unit of population, relevant size of population. Okay? So this is my unitless population, and this is my scale for the population. And I don't know this in advance. But based on these two statements, I would already like to write this expression in terms of x and tau. So what I will do here is also find out how to write dn and dt. So n is ni times x, and dn. Okay? My x is my variable, so this is ni dx. This is kind of doing a derivative for both sides. Okay, t equals capital T times tau, and dt equals capital T times d tau. So I'm going to substitute these things into the original expression. Actually, I don't want to erase that. So I'll keep going here. Yeah?
The n to the dn, you draw the left according to n and the right according to dt?
Yeah. It's like doing a transformation of variables. Okay, so I just substitute, right? Equals,
You're doing dn over dt?
this is the n over dt. Yeah. 1 minus, this is Okay, and I'd like to simplify this as much as possible. So remember, these are still free. I don't know their values. So I can decide that if I have ni equals to k, it will make this thing much simpler, right? So I have, and I'll already replace it, okay? No, I won't replace it yet. R x times 1 minus x. Ni cancels out. And I'd like to be left with dx over d tau, as simple as possible, on the left-hand side. And now I decide that t is equal to 1 over r. And I'm done. Okay, so I found out that the relevant scaling for the population is the carrying capacity. Okay? And the relevant scaling for the time constant is 1 over the growth rate. Here it it was in fact obvious that it will turn out this way, but it's not so obvious in other more complicated expressions. And then after I'm done with that, I'd like to check this. Okay, so what the dimensions of 1 over r are dimensions of time. Yeah. And indeed, t should be of dimensions of time because that's how we define it. T is a time constant, and the unitless time should have no units. Should have seconds over seconds or years over years. So in the end, when I find the relevant time scales, I should always check that things match. It will not always be 1 over r. It could be a combination of several parameters, and then it will not be readily apparent that this has units of time.
If the dimension of t is 1 over r, the dimension of 1 over r is time, and the dimension of t is time as well.
Yeah.
So it means that tau has no dimension.
Exactly. That's how I designed it, actually. So this is just verifying that what came out here is correct. Okay, it matches in terms of dimensions. Sometimes you might have a mistake along the way, or you don't identify correctly how to define t. So, and then you will find it when you check that the units cancel out. It's a good way of verifying that you're correct.
And it's the same with the population?
Yeah, it's the same with the population. So x should have been is designed to be unitless. So this should have units of population. So this was an easy system, but because you had one constant, one parameter that has units of population, and one parameter that is 1 over time. But sometimes there might be no one single parameter that has units of population. So you might find out that ni is defined as a product of 2 parameters. Okay, so this is the more safe way to do the non-dimensionalization. Okay. We'll take a 10-minute break and then come and do the next part of the lesson, the model, the population model.
אז מה ההבדל ביניהם? כאילו, אנחנו מדברים על ההבדל מבחינת היציבות זה לא מה שחשוב, נכון? חשוב כאילו הצורה של המערכת?
צורה.
אוקיי.
אבל בכל אחד יש תבנית אחרת של יציבות. בסל נוד תמיד זה יהיה נקודה יציבה ולא יציבה. בטרנספרדיקו גם זה, אחת יציבה ואחת לא יציבה, ואז הן כאילו זה יכול לראות כאילו הן מתחלפות ביציבות.
זהו, כי נגיד הפתרון אז כאילו זה יכול להיות פעם אחת שזה לא יציב ופעם אחת שזה כן יציב.
כן, יש כל מיני סוגים, אבל תמיד הזרועות החיצוניות יהיו עם יציבות הפוכה לאמצעי, כי יציבות היא תמיד צריכה להתחלף. לא יציב, יציב, לא יציב.
אוקיי, ואז תראית גם את כי זה הפריספל, נכון? אבל הטרנספריספל הייתה
קו ישר.
הפוך.
בדרך ליד הנקודה זה קו ישר, ליד נקודת המשחק זה משהו. Okay. The next thing I'm going to do is uh, introduce a model for insect outbreak. And we use this as an example for how to do how to analyze a one-dimensional system and find its bifurcation, how to non-dimensionalize the system, and how to interpret our results. Okay, so this is a model of how an insect called the spruce budworm um, infects forests of fir trees. Uh, so these are the main players. We have spruce budworm, we have fir trees, and it was developed for it was developed about the ecological situation in forests in Canada, where this kind of insects can infect the forest and eat all of the leaves and eventually kill all the trees within just a few years. So it was of interest how you can maybe predict this outbreak when suddenly a population of budworms uh, becomes exceedingly large and kills the forest. How can you predict it or prevent it, and so on. So the model was proposed uh, by Ludwig. I think, I don't remember if it was a single person, in 1978. And the basic assumption is that the population of the budworm changes much more rapidly than the population of trees. Okay? What happens in reality is that this outbreak can occur, I think on the scale of months. And once the fir trees are all killed in the forest, they're replaced by birch trees and later by fir trees again, by succession. So the assumption is the population of budworm changes rapidly. That is our variable. And the population of fir trees changes more slowly. And we will take the population or the anything associated with it, with the population of the trees, we will take as constant. In fact, it's not actually constant, it's slowly changing. And the complete model, it actually includes two variables. One is slow and one is fast, but you can kind of isolate the time scales. Okay. So this is based on the same logistic equation that we have seen until now. Okay, so K is the carrying capacity for the budworms, right? Amount of foliage, for example. So how many leaves they have to eat. Slowly drifting. And there is an additional term here that represents predation. That's why it's marked by P. Predation by birds. Mainly birds. So the assumption in the model is that the predation is a sigmoid that saturates at some value B. And according to this type of according to this expression, where A and B are positive.
Well,
Yeah.
can you explain again what B and C?
P is some function of n. P is a function of n. And P, oh, sorry, this is n squared. Otherwise, it's not so interesting. And B and A are parameters of the predation. For example, B is the fastest rate at which the birds, for example, can eat the budworms. So basically, we have here two regimes. Birds eat as fast as they can. They can. When the population of budworms is small, there is hardly any predation, and we could assume that the birds look for their food elsewhere. And there is some transition in the middle. So
N is the population of trees or
of budworms.
of budworms. Okay, and and
The trees
K
come here.
K is the amount of foliage.
Yeah.
Okay.
Generally, roughly speaking. So.
And when you say that it's slowly drifting, what do you mean is that we're basically assuming that it's constant, or we're also?
Yeah, we are assuming it's constant.
Okay.
But it's interesting for us to see what happens if for different values of k or different values of r, because it actually changes its values with time.
What is the A? You said the B is like how
Okay,
fast
so
it is.
so A would control, I think, where this transition occurs in the slope. I guess. Let's see.
Okay.
We can check for it. So. Uh, mm. And then I'm asking is
A
when
squared.
is this maximum?
A squared plus n squared in the denominator.
What here?
Denominator. In C.
N, right? Yes. Okay. I'm asking when is this maximum? And okay, I'll need to do this again. So to derivatize again. Okay, I'll leave it here for now. But to check where this happens, you want to find where the derivative is maximal. So you're looking for the second derivative's intersection with 0.
Does it have like a biological meaning, like a physical meaning, as it says?
Yeah, I suppose it should have.
It should. Okay.
Can you explain what is K again?
Say again?
What is K?
K is correlated with the amount of foliage,
The number of
leaves, the area of leaves in the
so
forest.
it's slowly drifting, but it's the insect eating
What?
the insect eating this leaf.
Yeah, but it's drifting also not due to the insects. Okay.
So, but the K is dependent
On the insects.
on the number of insects also.
Yeah, yeah.
It's not
So,
from.
yeah, so I think we assume that as long as the insect population is low and we're not in the outbreak situation, they don't consume much leaves. Once there is an outbreak, it's kind of they would affect K more slowly than they multiply. So first they multiply, and then K will start going down. Okay, so we'll kind of reach an outbreak situation, and then K will be affected. But we're interested in when we reach the outbreak situation. And outbreak situation, it's kind of abstract for us now because we realize that n should go from small to large at some point, but we don't know what small and large mean, what the scale is, okay, or how abrupt this will be. The first thing we do is shift to a dimensionless equation. So we look at the variables and the parameters, and we know that the dimension of n population is equal to the dimension of k, and also to the dimension of a, because we add them here, add their squares. So they should be of the same dimension. Okay, and okay, so immediately we see
Why A should be the same dimension?
what?
Why A as well should be?
Because here we are adding a squared plus n squared. If we are adding them, they must have the same dimension. So if we look for some dimensionless population S, it could be n over k or n over a. We don't know what's best for us. And there might be several ways to do the non-dimensionalization. Okay? But some of them will be more beneficial for us. So here I will show how to do it in the more heuristic way, trying to direct myself to an advantageous outcome. And what I will try to do is to take all the parameters out of the sigmoid function. Okay, I consider it as the more complicated function for me. I would like to have something like this as my sigmoid. Okay? And then I care less about what I'll have over there in the inverted parabola. I don't know this, but I know that this is hard. I mean, like you asked, what is A and how does it control here? So I saw already that I had to take the derivative twice, and it's a bit complicated. And so I'd rather not analyze this term. I'd rather have it very simple. Okay? So this is so while simplifying this term, things will go into this term or into the time scale. Okay? And they might make things a bit more complicated, but I'm willing to pay that to have the second expression simpler. Now, note that no matter what I do, this will always stay a sigmoid, and this will always stay a parabola. I can't change that unless I define something square, but then I have to change this as well. Okay. Okay, so I tried to take the sigmoid and make it more simple. First of all, I will try to take out this a square. Oh, sorry. Here. And you see that I can have n over a squared both in the numerator and the denominator. So I'm quite sure about the best population scaling for me. Now, let's write this again. Let's write the whole equation again with this new substitution. I have the b remaining. It still annoys me. So I'm going to divide by b. I have a over b dx over dt equals r a over b. Okay, I'm done with simplifying the second term in the equation, right? I have this appearing, a over b appearing here and here, but I don't want to do anything to it because then I'll have to put it back here. I don't want to divide by b over a, for example.
Was that sign here? No.
What?
It was minus b.
Yeah,
Bn.
yeah, sorry. Okay, I did this out of my head. Okay, so I don't want to divide by a over b. I'd like to still simplify things. So I will try to put b and a into the time scale. Okay? I will write d tau equals b over a dt. Okay, so now dx over dt over d tau is ra over b. Now I have several parameters remaining, but I note that I don't actually need all of them, right? Because r never appears alone. R is always multiplied by a and divided by b. So what I'll do now is group together the remaining parameters to make the expression more simple.
How did you get to the a dx dt? Where did you take this from?
For
The first four.
this one,
Mhm.
because when I tried to simplify the sigmoid, I got that I want n over a to be my new variable x.
Okay.
So x equals n over a. So n equals ax. Everywhere I have n, I can substitute ax. Okay, and dn equals a dx.
Okay. So, but the tricky bit here with the dt, I didn't understand it.
Which one?
The
Here?
a dx
Here?
dt.
So there was dn over dt. And dn is equal to a dx.
Mhm.
Okay, before I group the parameters, I can also check whether my units are correct, whether this was a transformation that indeed gives me a unitless time. So let's see the units here. We said the units here in the numerator are, in the denominator, are population squared, right? So the units of P of n are units of B times units of population squared divided by units of population squared. So this cancels out, and we get that the units of B must be equal to the units of dn over dt. So this is just, let's say, I invent a unit per day. Just kilo worms per day. Yeah. Okay, so and the units of A are equal to the units of n, and that's just kilo worms. And my new variable tau, that is equal to B over A times T, if I check for its units, this is kilograms per day over kiloworms times day. And everything cancels out. Yeah.
Explain how did you write the units of B equal units to your right?
This one?
Yeah.
Yeah, because P is a component in this equation. Okay? So indeed, tau is dimensionless time. So this was valid. I don't always have to shift to dimensionless variables, but it's more convenient. Okay, now as for the parameters that I'm left with, I'm left with this and this. Okay? So I would like to rewrite the equation while defining new parameters. So I will define rho equals RA over B, and I'll define lowercase k equals K over A. Now we know that K is dimensionless because we know these two are population. And maybe we don't know exactly about rho. So the units of rho are equal to the units of R should be 1 over day. The units of A should be kiloworms. And the units of B are kiloworms per day. And indeed, rho is also dimensionless. So if I write the equation again, I get dx over d tau this is the non-dimensional form. The variables x and tau are non-dimensional. And the parameters that I'm left with, rho and k, are non-dimensional. And I can interpret them because I already know this form of the logistic equation. So I have this k that is my effective carrying capacity in the non-dimensional form. It's actually the carrying capacity divided by A, which I know is tied to the predation rate. So it's as if I'm saying, okay, the relevant carrying capacity here is how much the original carrying capacity is say higher than the onset of predation. Okay, say the original carrying capacity was 200 kilo worms, and the predation onset was 100, and then so the effective carrying capacity is 2. It's twice the predation onset. Okay. It's a scaling of the system. Instead of talking carrying capacity, I'm talking of carrying capacity with respect to the predation onset. Yeah, actually, it wasn't so hard. P of A equals BA squared times 2A squared equals B over 2. So A is the onset of predation. Okay. Yeah.
Explain again the relationship between K and A, and why would you experience that?
Yeah, I found out that when I non-dimensionalize the equation, the term that is equivalent to the logistic equation has as a carrying capacity not the original K, but K over A. So this is the relevant carrying capacity.
But A isn't unit vector.
No, A is, so it's as if, yeah, it's as if I moved to speaking about the population in chunks of the onset of predation. So X was, remember, X was N over A.
Correct.
And the new K is K over A. So they are both scaled by the same factor. Okay, so K is the carrying capacity when you speak of X, when you speak in terms of A. So K is equal to K over A.
Which means that K is also situated on the X or N axis.
Yeah, that. Mm-hmm.
And
So the capital K was situated on the N axis, and when you non-dimensionalize, you kind of scale the N axis. So now.
oh, you scale K the way you scaled N
Exactly.
by A.
Yeah.
Right. Oh.
Okay, it's the same scaling.
And P is a function of A that you now wrote?
P is a function.
Like what you just, the last thing you wrote?
Yeah, so I substituted A
Ah.
for N, okay?
Mhm.
So A is indeed an onset. This is what I tried to find out before, and it was complicated.
Why did you decide that small k will be capital K divided by A and not the opposite
I
divided by
wanted
logistic?
it to be analogous to the logistic system. Okay. Okay. I'll erase this. Now I can analyze the system, and it'll be more simple. So you have here the original system where P is given, and you can see here there are less parameters. We have only 2 parameters. Okay, so from a system where we had 4 parameters, and when you try to study the system, you start substituting for R and K and A and B. So you have a 4-dimensional space to cover, but in fact, it's not relevant. You only need to vary rho and K. Only vary the relations, these relations. Okay. So this is a simpler system, and we'll start to analyze this the way we did for all the other one-dimensional systems.
So rho is not a variable? Sorry, x is not a variable?
X is a variable.
So we have x as variable and rho also?
No,
Or
X is a variable.
now constant?
Rho is constant, and K is constant. Or it's a parameter. It's something that in a given system it is constant.
Okay.
But you would like to ask, how does this look for different given systems with different rho and different K?
Mm-hmm.
How does X change? So x changes very quickly, but the ecological situation might give you a different row in different times of the year, or so on. So we try to analyze it. First of all, we look for fixed points. There is a trivial one at x equals 0. We always have it. Okay, now to find the other fixed points, we demand this and we have this equation. Now, we already took care of x equals 0, so we'll do this. And now we have to compare these two expressions. And we do it by the graphical method. The first expression is a line. Okay? It intersects the y-axis at x equals rho. Right? When x equals 0, this is just rho. It intersects the x-axis at k. This is just a line. The other function, at very small x, we can neglect x squared from the denominator, and it behaves like x, like just this line. When x is very big, we might be able to neglect this 1, and it will behave as 1 over x. So this is a fast way of plotting that. And we are asking, where do they intersect? Now, the answer will be different for different values of rho and k. And now you see the advantage of having rho and k only in this part of the equation, because this one stays put. It stays the same no matter the parameters. And then when you change the parameters, you just change the slope or the intersection of the line. The slope is 1 over k. Rho is rho over k. Okay, so where do they intersect? We will look at different cases. Our first case is the case of small k. I'll draw the sigmoid, not the sigmoid, this more complicated function in black. And then for a small k, say here, there will be only one intersection, no matter the value of rho, right? So these lines show us the function for different values of rho. So we have only one intersection. And you can ask, how small is small k? So first of all, we can ask, where is the maximum here, right? And to do that, you would try to differentiate. And you will get x equals plus minus 1. Of course, minus 1 is irrelevant. But this maximum here is at x equals 1. So k on the order of 1 should give you should give you one intersection. And if k is larger than 1, then probably a bit larger than 1, you'll probably still get one intersection. You can also calculate at what point this does not hold. Okay. So small k. We have two fixed points for any row. One is at 0. We already dealt with that. And the other is at some small x here. The second case, we'll do it here, is when k is large enough, and we have this function, or let's do it. Okay, when k is large enough, then the line intersects the x-axis, say here, okay, past the inflection point. And then the number of fixed points, number of intersections depends on the value of rho. Okay? So for a small row, we get one intersection here. Okay? So we'll draw lines for increasing values of rho. This will be a range called alpha. And when we try to plot the phase portrait for this, it should look like this. Because remember, the function, the dx over d tau, is the line minus the sigmoid. And it's not the line, it's the parabola minus the sigmoid, but we divided them by x. So now it's a line minus this thing here. So the line is higher at this range here. So, sorry, x dot, not x squared. So x dot is positive, and the line is lower than this shape in all the rest of the range. So x dot is negative. And this is our phase portrait for values like alpha. If we increase rho a bit, we will get to a critical point where we have two intersections. We'll call this beta. Okay, so here we have a half-stable fixed point. When we increase rho even more, we will get three intersections, 1, 2, 3. We'll call this gamma. Yeah. I'd like you to notice that the stability of fixed points always alternates. So you have an unstable fixed point next to a stable one. Okay, always. Even when you have a half-stable fixed point, its unstable side will point to a stable fixed point. Okay, so this is gamma. If we increase rho even more, we will get to some critical point where we are tangent to this hill. Call this delta. No. So the alternation of the fixed points can also be used to check that you are correct, right? If you are somehow plotting a phase portrait and getting fixed points that do not alternate, you should check yourself.
Why? Always have to?
Yeah.
Sorry, what is it always happen?
Fixed points are always of alternate stabilities, neighboring fixed points.
No matter.
What? Yeah, no matter the fixed.
This is just assuming that you have like continuous.
Yeah, everything here is continuous. Okay, I increased R even more to a range that I call epsilon. And here I get only one intersection, so delta epsilon. Okay. Here I get only one intersection. In this series of phase portraits is what you should do every time you have this situation where a parameter can give you, changing a parameter can give you different numbers of fixed points. Okay, now when I have a series of phase portraits, I can try to draw some bifurcation diagram. Okay, so for large K, I can treat rho as the bifurcation parameter and try to draw a bifurcation diagram. So what do I have? I have an unstable fixed point at 0 for any rho. And for a small rho, alpha, I have one stable fixed point. When rho is beta, I have here a half-stable fixed point, and as I increase rho, it starts diverging into two fixed points. So this is a saddle node bifurcation. Okay, this is beta. Beta is a value, a critical value. Alpha is a range. Then gamma is a range. A range in which I have actually 4 fixed points. You can count fixed points. You can count there. At delta, this is another critical value. The two middle fixed points converge. and another saddle node bifurcation. And for the range epsilon, I have only the 0 and the high fixed point. So this is my bifurcation diagram. It has two saddle node bifurcations. Now, I'd like to give the names to its branches. Okay, this will be called A, this will be called B, and this will be called C. I kind of give names to the fixed points. I have the fixed point at 0, and the low population fixed point, the high population fixed point, the unstable fixed point called B. A is called the refuge level. And C is called the outbreak level. B is a kind of threshold for the outbreak. And I'd like you to note that gamma is a bistable region. It has two stable fixed points coexisting. So we could imagine that if rho is very small, the population does not go into outbreak. It's stable here. If rho is intermediate, it's in the bistable region, there is a possibility that if the population is suddenly increased, for example, maybe the birds go away, maybe they are hunted down, then the population will increase and go past the threshold into the outbreak level. Now, when I say the birds are hunted down, I mean something that is not part of the dynamics here. It's kind of a perturbation, some external interference that will increase X very rapidly, okay? Like a migration of a lot of budworms into the system. So we are here, and we need some noise, some perturbation to go past the threshold. But once we go there, we will settle here, and that's an outbreak. Also, if rho is very large, we can only be at outbreak level. So you could imagine that if rho changes with time, then it might go from this range, where A is stable and the population is low. Suddenly it goes past delta, and we have an outbreak. Okay? Yeah.
The bistable region, whenever we get a perturbation which is bigger than the threshold, we kind of automatically go from
Yes.
the first stable point to the
Yes.
right. So there's only one direction
No.
perturbation can affect us in gamma.
But a reverse perturbation would also allow you to go from outbreak to here. Okay. The worrying situation is that when, for example, when you start with the low rho and you increase rho and you get to the outbreak, as you decrease rho, say you don't have any perturbations, you decrease rho and you go back past delta, and you're thinking the first should be safe, but it's not, because you stay here. You must go past beta in order to go back to the refuge. And this is the hysteresis, right? I can mark it here. So if we started with a low rho and we increased it, and then we went past delta, and our system settled to the outbreak level. If we decrease rho, say we treat the forest, we use pesticides or so on and so on, I don't know what exactly affects rho, but if we try to treat it and we think we go back past the critical level, we've not remedied the situation because we are still on the stable fixed point here. So we will have, and we are there because of the way we reached it. Okay, because this is the hysteresis. we will have to decrease rho until this point in order to get back to the refuge level. Okay, this is about the hysteresis. Okay. We have just a bit more that I want to show you because your third question of exercise 2 deals with a similar case, okay? And I'd like for us to see this before the end of the lesson, before you try to tackle this exercise to its end. Now, I did a bifurcation diagram. I got that for different rho, I get different situations. But everything is also a function of k. So I can try to look at all the situations on the k rho plane and try to see what I get. So I know that for large k, I got a region of 2 fixed points, and then a region of 4 fixed points, and then again 2 fixed points. Okay? And for small k, I only had 2 fixed points. Small. So there are different regions here. For example, there might be some region that we would call bistable. And this region of 2 fixed points we would call outbreak. And this would be called refuge. And this, well, this would be refuge for small rho and outbreak for large rho without a bistable region in the middle. Okay? So you could also go from refuge to outbreak through here. But we don't know the exact shape here of the bistable region. And if we would try to calculate how many fixed points we have for each combination, okay, we have this, right? Rx1 minus x squared, or 1 plus x squared. And we would like this to be 0, right? So I can divide by x. But still, if I want to solve this, I have to multiply by a square term, and I have this here. I'll get a cubic equation, and it's a little difficult to deal with. So we have a workaround for this. Instead, we will try to define the fixed point as a function of r and as a function of k. Or, sorry. Remember when in the system I showed in the beginning of the lesson today, we found the fixed points in an inverse way. We found beta as a function of x. So now we would like to find k as a function of x and r as a function of x. Each fixed point, okay, x star, might be a function of k and r.
You mean rho?
Rho, yeah. Each fixed point, originally it should be a function of k and r, its value, right? Like we did here. X as a function of rho and of a large k. It gave me a curve. But I'm saying that this is pretty complicated to find. This is also rho. This is k. This might be complicated to solve for x as a function of k and rho. So what I'm saying is I might be able to solve for k and for rho and then plot it. And So what we are trying to plot are the borders between the regions, between alpha and gamma and epsilon, the borders between different numbers of fixed points. So each critical point like this is a bifurcation point, where suddenly we have two fixed points appearing from here to here, or disappearing in a saddle node bifurcation. So I'm looking for bifurcation points. So a bifurcation point, the first condition for it is dx over d tau equals 0, right? A bifurcation point is a meeting of fixed points. Okay, so fixed points obey this, and then I will have rho x times 1 minus x over k equals x squared over 1 plus x squared. Right? This might be a little hard to solve, but I have another condition that the two curves are tangent. Let's see if we have still a plot of the two curves. I'm not sure. That the two curves at the bifurcation point, remember they meet and they are also tangent to each other. This is the rho equals, that was beta, that gave me a bifurcation. So I have two conditions. So to solve this, I will differentiate this and differentiate this according to x, and then solve. So this is condition number 1. From condition number 2, okay, condition number 2, we get that c over dx of rho x 1 minus x over k equals d over dx of this thing. And what you get from this is a condition for r, rho, sorry. So the tangency condition only happens for combinations of x and rho that give you this.
How come the K disappear?
How did k disappear?
Yeah.
Oh, yeah. Because you first, you do the derivative of this times this, and then this times the derivative of this, and you get the minus rho over k in the both of them. Okay. I leave these things for you to solve at home, but from this row and from condition 1, you get k equals 2x to the third divided by x squared minus 1. So here you substitute an expression on x instead of rho, and you are left with a solution for k. So you have two expressions, k at the bifurcation point as a function of x, rho at the bifurcation point as a function of x. What? It's also for delta. In delta, there is also a tangency because, okay, here.
Okay, so yeah.
Okay, so what we get is allows us, I'll put this on the internet, the plot, allows us to get some curve here. marking the bifurcation points. And because you can make a table. You can give values of x and get the values of k and the corresponding values of rho, right? So if you have an x and you put it here, you get rho. You put it here, you get k, and you get a point. So x equals 1, and so on and so on. This is confusing. Until x equals, I don't know, 100, you run over this curve. This is called a parametric curve. Okay? Parametric curve. K over x. Yes. K of x, rho of x. Okay. I'll just say that the meeting of two curves here tangentially is called a cusp point. And if you plot the fixed points here, you get some interesting shape of a surface. And I'll put this on the web so you can see. I was going to show it with my computer. I think that's it. Maybe I'll go over this and show you the images in the beginning of the next lesson. But this is something that you should know the method. I mean, setting this condition and getting the parametric relations. Okay. If there are problems and questions, you can write me an email, and I'll try to explain.